Thank you so much for attending my call. Who am I? Of course, you have to introduce yourself. I'm a principal security consultant for BSI. I specialize in cloud-native orchestration technology security assessments. I also specialize in red and purple teaming and general penetration testing. So these are the area of my focus. The agenda, the talk today, I'd like to, the agenda is initially to introduce the Kubernetes, basically Kubernetes 101, just to make sure that everyone is on the same page in terms of what Kubernetes is and why we need Kubernetes or why we use Kubernetes. And then we'll talk about the Kubernetes architecture, how the Kubernetes architecture is put together, what component does what, and how, as a whole, Kubernetes works. Then we'll talk about the Kubernetes deployment, on-premise security risks, some of the risks that we tend to see during a security assessment, in particular when it's deployed on-premise. We then focus on the Kubernetes core access control list, so how the access control works in Kubernetes environment, and with the focus on role-based access control list, RBAC. Following that, then I will transition to cloud architecture in Kubernetes, with focus on Azure Kubernetes architecture, and finally I'll discuss the Azure Kubernetes security risks. Some of the when you deploy Kubernetes in Azure, what are the security risks and what you see by default and what you could do with it, exploit it, etc. So it's a lot to go through. So basics of Kubernetes. What's Kubernetes? It's an open source orchestration system. It essentially was developed by Google internally. They were using it internally, and they made it open source. Orchestration at the basic level, essentially, it's basically you manage containers and in kind of independent as an independent unit, so you can orchestrate quite large number of applications using orchestration techniques, which is that could apply to Docker and other container engines as well. Why do we use it? Why Kubernetes? What problem does it solve? This is not actually legacy of way of doing serving deploying an applications in one particular unit. It's focused on a kind of a microservices. So each container has its own independently as a unit. So they independently work. Essentially it's a smaller independent unit as opposed to having everything in one unit. So with in Kubernetes or in container world, you can have your applications or your services independently deployed in individual deployable service, and you can obviously scale up, scale down using Kubernetes and containers in a large environment, making it it's easy to scale and it's easy to actually tear it down. Understanding the Kubernetes, I think it's key to understand the architecture, how Kubernetes actually put together in the first place. So at a high level, in the center of every Kubernetes environment, you have the master API server, which is the core control panel of Kubernetes. Within the master servers, you have other components within the Kubernetes. In particular, etcd, which is the database for Kubernetes API server. And you have a scheduler, which essentially it schedules, it waits for pods to come live, and then it pushes those pods to a worker node. And then you have the kube controller, which manages number of processes. So node processes, service accounts, endpoints, controllers. And then you have the kubelet, which is, kubelet is an agent, runs on a worker node. And a worker node, essentially, you can see it as a server that basically manages your workload. And the kubelet's responsibility is to making sure the containers that are running fine, if they are running fine, it's okay, because kubelet and master API, they communicate at all time. If a container goes offline, kubelet's responsibility to basically report that back to the master API and therefore schedule a push another a pod onto a workload. So the key point here is that to see it's in each of these you have the certificates. One of the way you want to see this in Kubernetes environment is that it's similar to kind of a client and server. So in this instance, the components are considered the clients, and in the central of the Kubernetes is the server, which is the master API. So the key observation is that whenever you deploy a Kubernetes environment, you also have the responsibility to generate those certificates. So imagine if you, from a security perspective, you don't have those certificates are generated if it's not done correctly. And naturally, if you are using kubeadm or a cloud services, those certificates are already generated for you. But if you are deploying this on-premise, which we see quite a lot of places, if you deploy a Kubernetes on-premise, those certificates essentially you have to actually generate it yourself. And there are obviously cases as well when you want to not use, let's say, kubeadm's certificates, that you want to generate your own certificates. So the client and the components are the clients, which is the etcd kubelet and the rest of it, and the core components of the Kubernetes is the master API server. There are risks, of course, when there are no certificates are generated in terms of the authentications, encryptions, as well as encryptions in terms of in transit as well as at rest. So some of the issues when we see that when you deploy a Kubernetes on-premise on bare metal, issues that you will see, there are no TLS and there are no client authentication. So what happens is when there is no TLS and no authentications, by default, Kubernetes API server runs on port 8080, which means that on its own, it's actually not secure because it's HTTP. And in terms of authentication, you can just use, for instance, command here, that you can just list all the secrets, etc., etc. So it's in terms of client authentication, and there are no client authentication, and there is actually no TLS encryptions as well. So imagine if somebody's actually, just you have this deployed, and people could easily access if they have network access to that environment, which is actually quite common. The risk with that in terms of no encryptions and client authentications, you can, for instance, if you don't have authentication enabled, you can just list all the secrets here. As you can see here, it's like on a port 8080. By default, port 8080 is not HTTPS. So an attacker could actually essentially intercept traffic as well as authenticate to Kubernetes directly. The mitigating Kubernetes in terms of client authentication and HTTPS encryption. What do you initially really, as a kind of administrator or as a security assessment, is that the first step is really to generate a certificate authority for your API server. So the API server, it's essentially you need to do a CA. For using that CA, then you can actually sign other components of the Kubernetes services. So here I'm just generating CA. I just call this Steelcon. And the idea of using that CA to sign all the authentication as well as the encryptions in Kubernetes API. In order to mitigate, once you've kind of generated this CA, the next step is to really to go back to your API server to enable two things. One is the client authentication, as you can see here, from the client CA file, which specify our ca.crt, and the TLS files and the private key. So having every time when you generate a key, or every time you need to basically go back to your API server and reconfigure your API server with the right flags and right flags and the right certificates for it to actually work. Once you've kind of configured the API server and generated the right key, mitigating it, now if you're authenticating to API server, you no longer can just curl, HTTP, the Kube API server, port 8080. Now you actually have to have the right certificate servers, so such as, using the TLS certificates that we've generated. And then you basically run your Kube API server with the certificates that you've generated. So at this point, the Kube API server, it's no longer, no longer listens on just a clear text and client authentication. So once you basically once you've kind of enabled your authentications, the next step is to that for administrator or for client to authenticate to API server, they need to have a certificate as well. So they need to have a client authentication, client certificate for it to authenticate the API server. And in this screenshot, what I'm doing is I am creating myself a certificate, Sadi Zane, by using the CA that I've generated initially, and I'm signing my certificate using the CA certificate that I've generated. And I am here essentially using the certificate connecting with the certificate. I'm connecting to the API server itself. So as you can see, I'm using OpenSSL, and then on the bottom of the screenshot, I am doing kubectl get secret. Essentially, I'm requesting a secret, but this time I'm specifying the certificate file. So I'm saying actually authenticate to API server, but make sure that you are using the right key for it to authenticate. Without those keys, obviously, you're not going to be able to authenticate to API server. The other components of the other risks of Kubernetes on-premise deploying Kubernetes on-premise is that one of the core components of Kubernetes is etcd, which is the key value database. Essentially, every configurations of API server is stored in etcd. So if your etcd is compromised, essentially your entire API server, entire cluster is compromised. So what essentially you want to do is you also want to make sure that your etcd database is secure with appropriate key, as well as authentication between etcd and the API server is secured using TLS as well. So by default, when you run etcd server, etcd server could be actually could use separate certificates. In most cases, the API server uses its own certificate, but also etcd also uses its own CA as well. But in this instance, I'm just actually using the same certificate for API server for demonstration purpose. So if you run etcd components of the Kubernetes, what happens is by default, again, it's on the port 2379. So that, you can even see it at the bottom. It says it's strongly discouraged that using, no HTTP or TLS encryptions as well as client authentication. So that, we see quite often in environments where etcd databases, left like this with no authentication or no encryption. So anyone can potentially directly connect to 2379 port and dump all the databases and, your secrets, etc., the things that you're actually protecting. because etcd, that's where the configurations and the data are stored. The etcd server itself as well, by default, as I said, there's no encryptions involved in terms of in transit as well as in rest. So if in this example, what I'm doing is I'm creating a namespace on my Kubernetes API server, client C, and I am using I'm basically using a generic a secret, creating a generic secret, and I'm pushing some sample data like client sensitive data to the etcd server. So what's happening here is that my data now, two things happened here. The secret is created in first instance. That secret is it basically transmitted in HTTP, so in clear text, and then secondly, it's the data itself. It's on the etcd database now. It's actually clear. So there are two kind of significant risks here. One can intercept, and the second is that somebody compromised your database, or they could potentially dump those personal identifiable informations. Just to demonstrate the actual the security risk with the etcd database when it's actually in clear text. So as you can see here is that, I've created the secret, and now if I have access to the etcd database, what I could essentially do, I can recursively look for that information that I've just created, so that particular secret. And now, because the information is actually in clear text, you see at the bottom, at the top, I'm looking at recursively, and at the bottom you can see that actually the information is still in clear text. It's not encrypted on that database. So obviously, from a security perspective, or from the best practices, you don't really want to have a database who's not encrypting your data in rest as well as at disk. So in this case, etcds have no encrypted data by default. So, in terms of client authentication with etcd database, is that so in order to actually mitigating the authentication aspect of the etcd, you still have to do two things. One is that you need to generate the etcd the certificates. So again, it's a component of the API server. So you want to create a TLS certificates for the etcd. This is what I'm doing here. I am creating the etcd.cnf, and I am once I've created the config file, essentially I am signing the etcd key with my CA key here, which is the ca.key I've generated for API server. So any components of the API, any components of the Kubernetes needs to still be signed by the CA that I've generated in the first place. But as I said previously as well, you can obviously, you can have separate certificate for etcd, which is a best practice as well. So I'm creating a certificate for etcd database. And once I've created the etcd certificate, I need to go back to the API server again, reconfigure the API server with the right certificate that I've generated for etcd server component, and then making sure that it has the right certificate in order for the client authentication between the API server and the etcd. It's actually done in a secure manner. So you constantly have to go back to the API server, actually reconfiguring those flags, which can be tricky, and the documentation with Kubernetes is quite tricky as well. For us to mitigate the clear text password, the clear text kind of information, so PPI data, sensitive information, we need to obviously encrypt that etcd database. This could be done, and using there's a number of ways actually encrypting etcd database. You can use kind of third-party providers, open source frameworks. But here I'm actually using a native encryption config kind type within the actual Kubernetes for me to actually encrypting the database of the etcd. So the steps are, I am essentially creating a random base 64, and then I am using the encrypt etcd YAML file, and I am essentially if you can see the kind type here, it's the encryption config, and the type of provider I'm using also it's AES, CDS, and then I'm specifying the key that I've generated. Once I've basically created the random base 64, AES CBS, and the right config file, essentially I can then go back to my API server, and then from the API server I can specify the encryption provider config file. So I need to specify the YAML file that I basically built with that using go back to the API server, reconfigure the 8CD with a correct flag, which is the encryption provider config, and then path to that 8cd.yaml. The observation is that if somebody actually does manage your APIs, gain access to your API server, and they have access to the 8cd.yaml file, and they could essentially decrypt your database as well. So that's game over if somebody somehow managed to gain access to API server. So because that YAML file does sit in your API server itself. Once you've basically once we've rebooted the API server, unfortunately, actually with the API server, you have to restart your API server every time you actually make those configuration changes. It's one of the downside of the on-premise deployment. Once you've basically created the encryption plan, etc., now because the database now is encrypted. If in this example, I'm pushing I'm putting some data into the 8CD database, some PII data, and if I look at the same time, I'm using the same technique recursively in the actual 8CD database, and as you can see, actually there's no clear text information anymore because the database now it's encrypted, so you don't actually get that clear text information again. So that's all secure in terms of 8CD database. From the 8CD also, as I mentioned earlier, that there are clear text informations that transmits between the API server and the 8CD. So anyone can actually be in the middle. They can intercept those sensitive information and essentially exploit or compromise your API server and the rest of your environment. So how do you go about? An example here is what I'm doing is essentially I am using etcd-ctl, which is a 8CD binary client. I am putting some data into a client A. I just call it secret. On the left hand, I'm using a TCP dump, just demonstrating man in the middle by doing a direct interceptions of traffic. As you can see, the actual data is actually sat here. So anyone can essentially intercept your sensitive data. So not only the client authentication, but you also want to make sure that your TLS encryption is done correctly between the API server as well as the 8CD. That's secure and not flying in clear text. Once you basically regenerated the certificates for similar to the API server, and reconfigured your API server with the right client, with the right TLS certificate. Now I'm doing exactly the same thing. I'm actually pushing some data on the client B secret. And then if you look at on the left side of the screenshots on the right here, that traffic no longer is actually in clear text. It's all kind of encrypted. So even if somebody has managed to encrypt your data, if they're able to actually intercept your data, then it's in clear text, so that no longer hopefully useful because it's encrypted. One of the core components of Kubernetes Kubernetes authentication and authorization is actually understanding how the access control works in the first place. Having some knowledge on the ACL first, then we can dive into more authentication, authorizations, how Kubernetes does all that in a secure manner. In this example here is that the way the ACL works in Kubernetes is that from a client, kubectl essentially a client that you can use to interact with API server with a Kubernetes, but that could be a user as well with the right certificate. But also from the pod and service account, they can also actually authenticate to or interact with your Kubernetes object. So every time when you interact with a Kubernetes API server, this is the step it's basically going through. First, it's actually go through the authentication. Does the user or the service account have the correct authentication? If that's the case, then it's the next step, authorization. Authorization essentially checks, if that particular user have the correct authorizations or roles, etc., to access the Kubernetes object. The third step, which is the admission controller, the admission controller essentially has the final say in terms of what you should be, whether you should be actually accessing a Kubernetes object or not. Admission controller answers the existential actually questions around DevOps, because that decides whether you've passed your authentication, passed your authorization. If you enable to admission controller in your Kubernetes API server, it would dictate whether actually that particular request should go through the final destination, which is reaching the Kubernetes object. Some of the example of the admission controller could be that checking your image. If your image is actually insecure, then it shouldn't actually pushing that image into your environment. Or if you have, let's say, there's your security context, or your image runs on the kind of a root ID or root account on that image, then admission controller could say, no, I'm not accepting this because that's not the right way. This is not based on my policy. I'm not allowing this. So admission controller has the last say basically. Some of the areas that, in terms of authentications on Kubernetes, there are multiple ways of authenticating. There's 509 client authentication, I've already mentioned. There's a stat token file. Yes, your information actually saved in a CSV file. There's Kerberos, where you can use in kind of Active Directory, LDAP authentication, and there's also the OpenID, such as you can use your Azure AD, Azure Active Directory to authenticate, and other open IDs you can use for authentication. The two that I'm focused on is the X5 client certificate. You have to have actually valid certificate and sign the right CA for you to actually authenticate Kubernetes API. And the second is the static token file authentication. We also look at the downside of those two. I've already showed that X5 client authentication earlier. Here I am creating a certificate for myself, Sadi Zane, and I am actually signing the certificate with the CA API service CA that I've generated. And as you can see, having the right correct certificate, I can easily use the get secrets, access the Kubernetes environment. So this is the client authentication. The static token, which is an interesting one, I've actually seen it used quite as well. The format of static authentication, it's basically your authentication essentially saved in a CSV file. So you have a password, a name, your ID number, and the group. So the password here is like winter 2022 $Zane, Sadi Zane, and the UID 01. So that the point is here is that actually with the static token file authentication, this information is saved on a CSV file, and that CSV file needs to be in your API server as well. So you need to go back to your API server and then point in your CSV file with the configuration, with that password in the CSV file, and then rebooting your Kubernetes API server. And as you can see, because I've got the CSV file here, I can just use that password directly interacting with the API server and listing all the secrets. So you really, if, for instance, that someone's managed to compromise your API server, take this CSV file, they don't need to maintain persistent they can just use that CSV file to authenticate to API server all the time, and depending on their user roles as well. So some of the downside of the disadvantage of authentications and certificate-based authentication, as well as the token-based authentication. Certificates are stored on disk. If there's somebody managed to steal your certificate, that's a bad day because you really can't revoke it. You have to reissue it. If someone's leave the company, you can't revoke it. That's the issue. And if you want to assign a new user to a new group, you have to generate a new certificate. In terms of the token-based authentication, tokens are in clear text and is stored on a disk. Someone accesses your token on the disk, there's a trouble. They can have access to that environment, but again, a token cannot be revoked. So these are the downsides of the actual token as well as client-based authentication. Authorizations, following that authentication, the authorizations in Kubernetes, essentially once the request is authenticated, once the user or service account provided the right authentication, then the next step is they need to go through the authorization. So what authorization is, there are a number of objects within the authorization, which is the always allow, deny, and RBAC and node. The one that we are interested in, the one that we use, or the one that actually widely used in production is the RBAC, role-based access control, which I'll be talking about this much more in detail. The RBAC is essentially policy-based control. So you can decide who can access what and what object, and quite granular control in terms of RBAC. Basically, RBAC, as I said, the focus of RBAC is regulating access into your environment. So in terms of RBAC, you can say, I want that particular user have that particular access with based on their roles and their permissions within the organization. So you don't give just access, admin access. You can actually restrict your access to that individual. You can go really granular in terms of access. RBAC could also be used in terms of a service account, not just the user as well. You can apply the RBAC concept into a service account that you create sometimes for automation and etc. There are key objects in RBAC. So the key RBAC objects are role binding, cluster role, and cluster role binding. The things to remember is that role is a set of rules, a set of permissions, such as allow, create pods, read pod, etc. And you have the role binding. It basically assigns that role to that particular role binding. So whenever you create an RBAC, you need to have a role or role binding, which they can basically, you can assign that role assign that role with a particular permission to a particular role binding on a specific namespace. A namespace, essentially, it's in Kubernetes is considered like a compartment that you can save, isolate your containers. There's also cluster role and cluster role bindings. The cluster role and cluster role binding, essentially, it's not namespace scope, so which means that if you have a cluster role and assigned to a namespace, if you have a cluster role and cluster role binding assigned applied to a Kubernetes environment, if somebody managed to compromise a cluster role, they can essentially access the whole a Kubernetes namespaces. So it's no longer actually one specific namespace, but you can access pretty much all other namespaces exists within API server. As it says, basically grant access to all the resources with a cluster role binding. So role and role binding is more like the service account, this user with this permissions, doing this and that. An example of the enabling RBAC, again, you have to go back to QB API server and set in the right flag, which is the RBAC here. Right here. And for example, demonstrating the RBAC, the power of the RBAC here, I'm applying the RBAC to a user. I'm using the CF SSL, so which is Cloudflare SSL, similar to Open SSL. And I'm creating myself a user called dev user. and generating a CSR and a key file for that user. And then I am basically, as an administrator, I can request a certificate for that particular user using that CSR that I've created here. So it's a CSR is here, and I apply that to the Kubernetes API server. Essentially, at the bottom, you can see that the certificate is actually created. But when the certificate is created, obviously you want to make sure that whether you want to approve the certificate, you want to see that certificate if it's right for the right person, whether you should allow or deny that certificate, which you can, using Kubernetes kubectl, you can look at that CSR. At the moment it's pending, and it's generated basically by the master. Just going it's essentially just generated by the master client, and at the bottom, and you can see that you can either kubectl certificate approve or deny that particular certificate. When you create a certificate for an individual user, you have full control of what to do and not to do. Following that, I can basically then create a role and role binding using RBAC. So the role here is that, as you can see from the essentially I'm doing kubectl get role, create pod. That particular role has the permissions of the resources is the pod that it can access, but also the verbs that it can have access to. So such as get, watch, list, create. So this particular role, if it's assigned to a right role binding, that individual will have actually, getting and listing a pod, or getting a pod, or also if you see that at the bottom it says pod exec, so you can execute into a pod, so you can have shell into that pod. Following that, once you create the role, you need also create a role binding, which is the role binding. What I'm doing here now, I'm basically outputting this in a YAML. So that my role binding is called read pods, and inside that read pods, there's a role which is specify the name of that. Inside that role binding, that you can specify the role that you created, which is the create pod, and then the user that you are actually assigning this role binding, which I've created the dev user here. So once you apply that, you can see a dev user as well. You can apply the role and role binding to that particular user. So that user should be able to only have, specific access to pods, specific namespace, but also specific verbs, such as listing a pod, as opposed to, giving all the access that he needs, which he needs. An example of, in terms of RBAC, we see a lot of overprivileged service accounts in on-premise as well as in cloud. If an attacker able to actually compromise a pod with an overprivileged service account, they can then obviously use that service account token, then pivot further into your environment. So I've demonstrated how this could be done. In that screenshot, there's a role binding in the middle, and there's actually just a pod I've created using the BusyBox standard BusyBox. So if you see the role itself, it creates the role's basically resource type is pod, and the verb is kind of a get, watch, list, but also that particular role has pod exec, which means that if that role is assigned to a service account here, which is the role binding, then if someone actually compromised that particular service account, they can essentially access that particular namespace, that role and role binding assigned to. So at the bottom, as you can see, I'm just creating a standard BusyBox, and I am assigning that service account to it, which is if you can see so the service account name, it's a vulnerable SV. So essentially this role and this role binding assigned to that service account. So once I've created that particular pod with the service account, here what happens is that the first screenshot, the first mark, it's basically applying those roles and role binding and creating the BusyBox. And the second is that, imagine if an attacker managed to basically compromise your BusyBox through application or any other attack vector, because this role and this service account is overprivileged, what they can do, essentially, they can just download kubectl directly onto the BusyBox and then directly interacting with your Kube API server. So they can directly interact to that namespace. So here, following that, they can then, exec into that BusyBox and using, basically, because that service account is overprivileged, they can just say kubectl because I've downloaded the kubectl client, kubectl get pod, and you have all the other actually microservices, which one of them is DockerSec. Because you have kind of a pod exec permission, you can then use kubectl exec into the DockerSec, because that's basically that service account is overprivileged. Then you can just jump from one container to another container in the same namespace using that overprivileged service account. So moving away on a premise on bare metal. Speaking of the basic cloud Kubernetes, it's one of the probably most of the organization actually now its transition is from on-premise to the cloud, and the cloud Kubernetes is one of the areas that managed cloud in Azure, particularly AWS. We see quite a lot of customers actually taking that approach, because it's the responsibility of on the cloud is that you no longer have to generate those certificates at all. You no longer have to do the basics of security. All this is done for you in terms of generating certificate, authentication, etc. That could be done through on your Azure AD or your on-premise AD, etc. So the architecture with the cloud in particular, the responsibility, there's a managed, or basically Azure managed, and there's a customer managed. So the customer has access to basically Node, the container runtime, essentially just the Node, the workload that you are running your application, whilst the cloud providers such as Azure, they managed all the key core components such as the master API server, its CD, control manager, etc. So you no longer actually have access to those components, the core components, which means you don't have to look at in terms of security, etc. So the security of that is controlled by the cloud provider. Conscious of time, so the issues around actually network and the issues that I see in a cloud environment with Kubernetes services, it's basically as follows: network security and network policy, secrets, and pod security policy. These are the areas that I come across, and we tend to kind of find over and over issues with that. One of the issues with the networking, and for some reason it's kind of in most cloud environment I see networking actually ignored for some reason. They think that just because they've used Kubernetes environment orchestration system, it's by default is secure. That's not the case. The networking is still part of your day-to-day, actually making sure that your network is done correctly in terms of traffic flow. With the networking, there's internal networking and external networking. The internal network within the Kubernetes is a traffic flow between the pods, between namespaces, etc. From external network perspective, it's where your basically workloads then connects to outside, so you're to the internet, basically. Some of the issues in network security. By default, your basically Azure's Kubernetes API server is exposed to the public. There is no restrictions on it, so anyone can actually access to your Kube API server. And if they can access to your Kube API server, there's a 0-day, for instance, so if they have a token, they can interact with the API server anywhere, because there are no restrictions, and then interact with your workloads, such as your containers, applications, and starts, exploiting, exfiltrating data, etc. So there is no restriction, basically, to API server. So in this example here is that I'm using the kubectl config view. I'm just listing my API server on the Azure managed Kubernetes servers, and I'm doing a quick, just an nmap scan from my box outside of the Kubernetes. as you can see, they ask obviously your HTTPS, which is the API server is running on, but also Microsoft thinks that port 9000 it's okay, security through obscurity, changing port 22 to 9000, hiding it in a way that thinking, okay, well, people don't see it, this is as an SSH. But if somebody have the right authentication rights, SSH key, etc., they can directly connect to it. The point is not just the SSH, it's the API server. Your APIs is exposed, and the API server is a REST-based API. So if you have the right token, right authentication, you can directly interact with it anywhere in the world. So I am demonstrating it here, just how an attacker would go about doing that. You have a container, and your container gets compromised, and attacker mounts the token, the service token, which sits in the Kubernetes service account token. You can mount that token, and then you can copy that token to your machine from the compromised box, and then using that token, you can directly interact with the API server. So attacker compromised a container, attacker mounts a token, copies that token to his machine, uses that token directly interacting with your API server. If you had restricted your API server, that would never happen, because even they have a token, they can't directly speak to your API server. How do you go about mitigating that? You need to restrict your API servers to the internet, which could be done in a network policy.
The API servers have a public IP by default.
Yes.
They do.
Yes. And it has, just a standard Azure IP. So that the mitigation is to restrict your API server to outside, making sure that it's contained. Just applying the same network principles that you do in your day-to-day. The other issues that we do is that accessing to the VM metadata within the Azure. So if you compromise the box, if you compromise a container inside the Azure cluster, you can directly interact with the VM instance metadata if you don't have network policy in place, which I see it over and over. What happens is an attacker compromises a container, and he and she basically uses the, downloads curl if curl is not installed, probably installed, and he uses basically metadata equal true, and the Azure's kind of a API server, metadata API server, and then basically dumps all this information. So in this instance, obviously, you just see private data, but in my experience, I've seen tokens, I've seen secrets are kept in the VM kind of metadata in Azure. So you're basically mitigating around that is to ensure that you are restricting from your network policy. You want to make sure that your Azure VM metadata is restricted, so which sits on the 169.254.169.254/32, because that's just one IP. So you can actually mitigate that as well, quite easily, provided that you have a network policy in place. The other issue is that once if an attacker have access to your cluster somehow, or gain, code executions or store a token, a certificate, gain access to one of the microservices. Between the microservices and if your network policy is not in place, what happens is that attacker could easily also use that as a pivoting point into your node. So in a node is a worker node. Essentially, that's where all your basically workload live. So if they can, because there's no network policy, or worker loads by default actually listening on port 22 SSH, they can also pivot from that container back into your workload. And if they compromise a workload, they compromise the entire, basically, clusters of microservices, because that's where their workload sits. It's on the nodes. Network policy, by default, there are no network policies, and if you don't enable it in the first place in Azure, you basically have to tear down your environment and go up again and enable a network policy. So if you are deploying your Kubernetes services in Azure, you want to make sure that you basically enable network policy in the first place. So areas that you want to mitigate, it's in the first place you want to have a network policy that isolates ports ingress policy. So all the basically traffic, incoming traffic from outside, you wanna stop that in the first place. Obviously not in productions. This needs to be done in a right way. And once following that, you can following that, what you can do is so this is the ingress policy, and then you allow explicit internet connectivity inside the pod, inside your cluster back to the internet. Because you used ingress, you basically restricted traffic coming in. You can then be in control which pod or which namespace, which workload to basically connect to outside using network policy. So you can just say, I want to be explicit in terms of specific port selector. So I can specify port A, port 2, from namespace, admin could go outside. The rest should, communicate internally only. And following that, you can basically then create a network policy that creates explicit communication between pod to pod and from namespace to namespace. Because if you apply the first two rules, ingress as well as the internet, if you fill in ingress if you apply the ingress, essentially what happens, your communications between each namespace and each pod actually also stops working. So you need to be, finally, you need to be explicit in terms of communication between this namespace to that namespace, from that pod to that, pod A to the pod B, because otherwise things would actually stop working. The Azure Kubernetes, by default, secrets are not, they're basically base 64 encoded. There's no encryptions. So your secrets, if somebody has access to a configuration file, authentication, they can just do kubectl secrets, dump all your secrets. And as you can see here, I'm creating a standard secret using the native Kubernetes secret management. Essentially, is a base 64. I'm creating an admin here and then a user, and I am applying the secret. I called it database secret. And so, if somebody accesses to this configuration file now, they can also decrypt that quite easily using, just output that to base 64, and then you have the clear text back. So the recommendation is when Kubernetes calls this secrets, actually it's not secret, it's a base 64. So my recommendations, or recommendation I tend to apply to my customers are, make sure you actually use, cloud providers, secret management in AWS, aka Ski Vault, or GCP if you are using GCP, or third-party open source, CyberArk, Conjure, HashiCorp. These are actually alternatives that you can really manage your secret in a kind of a secure way. Discuss this. And the aspect of the issues that we tend to see in cloud deployment is that lack of PSP, so port security policy. So in particular, issues that we see that containers are running in a high, it runs in kind of a high privileged UIDs. So such as if you just deploy using kubectl and then bring in an image from a registry, a kind of a repository, your image will, if you don't have a PSP or your security context enabled, basically your image will run in a high kind of a privileged ID, so such as UID 0. Obviously, you don't want to have your pod or your containers run with that. Well, that's obvious reason, because if somebody compromised this, they could escape from that. They could do a lot of this, maintain persistence, etc., etc. So the alternative to that is that you can apply security context, PSP, port security policy, which is essentially you can either do it in the container level or at the pod level. At the container level, you can enable, specific UIDs. So you can say UID 1000 instead of actually giving it UID 1. And when you run that, as you can see, when I create a new pod with a PSP security context enabled, and if the last screenshot that you can see, that is actually the ID is no longer the UID 0, it's UID 1000. So it's running under a different user ID. I think that was all. Apologies, Kubernetes is quite actually hard. It's complicated, but yeah, I tried my best to describe it as everything in an hour or less. Any questions? Or you can catch me afterward. We can definitely talk about it. That is.